Voice of the Sea, learning from experts across the ocean.
Welcome to Voice of the Sea.
In this episode, we're with University of Hawaii researcher Hilary Close, examining very small, suspended particles in the open ocean and their vital role in the food web. Recent research suggests that these particles are critical to the production of commercial food fish. In order to collect enough particles for study, Hilary pumps thousands of gallons of water through tiny filters. The filters capture the suspended particles, which Hilary can then take back to the laboratory for analysis. So Hilary, you have a whole rack of large equipment that I watched you roll onto the ship, and can you tell me what they're for and what you're doing?
Absolutely. These are just sampling units. We're filtering just lots and lots and lots of water. And we're doing that in place, so we send them down on a wire, down to whatever depth we want in the ocean, and it just sits there and it pumps the water right in place. We're basically capturing all of the very, very tiny organisms, so microscopic organisms, bacteria, things that we're not going to catch in our other modes of sampling. So you could not catch these in a net. You have to just filter lots of water to get them. You can sort of think of seawater as like a vegetable soup or something. There's a lot of stuff in there, but most of it is stuff that you can't see. So it might make the water a certain color, but you wouldn't see what's in it until you look under a microscope. And that's everything from bacteria to tiny little plants, and then all of their dead biomass too. That's actually usually a larger part of what you find in the water is just the dead biomass of all of these things.
And what will that help you to know about the ocean?
Two things. It's how does the microbiology respond to changes in its environment, or how does it operate in different seasons? We're sampling in different seasons, but we're also looking for that link to how their biomass might feed into the larger food web. So that's why it's great that we're looking at all of these scales at the same time, from very, very tiny particles to little zooplankton up to fish. And we're looking for where the linkages are. And we have some of the chemical tools we use are very specific to address that. They're very kind of cutting edge measurements that we're making that can make that connection.
Maybe you can show me how your equipment works, and then what is the product that you're going to then take back to the lab?
Yeah, so I mean, this whole operation is actually mostly just kind of the battery power and the motor. My sample is actually just sitting here, so it's at the top. It stays protected from all of the machinery. It stays very clean. And what we have is we just sandwich a flat filter in here, and we can actually do a couple different tiers so that we can filter out coarse particles first and look at them separately from the finer particles below. And when I say particles, of course, again, that's dead biomass as well as actual cells. So bigger cells, bigger particles, smaller particles as well. The water just comes in here, goes through however many filters we have, and then the rest of it is just the pump that makes the action go.
I see. So the pump's just drawing the water through the filters.
Right. It's all kind of this passive, nice, gentle filtration. So we get really high quality samples this way.
You said lots and lots of water. Can you give me a feeling for how much water you're talking about?
So we usually look for somewhere on the scale of 1,000 liters, which, do a quick calculation, is several hundred gallons of water, and that's one sample. And then, so one pump, one sample will have 1,000 liters, and then we're putting all 5 pumps, different depths on each deployment. We're doing 6 or 7 deployments. So our total water filtered is going to be very impressive, like 35,000 liters or something like that.
Oh, wow. And how long would it take to filter one of those 1,000-liter batches?
So we send them down for 4 hours, which is kind of a nice, it's a lot of activity on deck, and then they go in the water, and then you sit there and twiddle your thumbs for a few hours, and then they come back up.
And so will you put all 4 of them down, or you have
5 of them, yeah.
Simultaneously?
Yeah, we just put them in sequence on the wire. We just space them at whatever interval the depth is that we want to sample at. So I think our deepest sampling depth is 1,500 meters, like about a mile. So It's pretty cool when you think about it.
Absolutely.
There's not much down there. That's why we would prefer to have even larger samples.
What's like the most satisfying aspect of being out at sea collecting your samples?
Okay, I would say I know exactly what it is with these samples specifically. When you bring this in and open it up and you see different colors from different depths. So you'll see nice green filters from the surface ocean where there's photosynthesis, and then you go a little deeper and it gets a little more brown but still green, and then it gets brown and sort of tan, and then sort of this very light color where you get less and less. So you get that initial first idea of what the samples are going to be representing. Although you can't always go by that because a lot of what we analyze is not pigmented. It's invisible, but it's a kind of a first impression, very satisfying.
Next, we catch up with Hilary in the laboratory at the School of Ocean and Earth Science and Technology, where she is analyzing different forms of the element nitrogen to track the path of suspended particles through the ocean food web.
So the last time I saw you, you were filtering massive amounts of water. You said something like 350,000 liters or something like that by
total,
the time
yeah.
you're done?
By the time we're done with all of the filtering on all the cruises, yeah, we will have gone through something like a swimming pool size, Olympic swimming pool size. For an individual sample, we're talking somewhere around 1,000 liters, anywhere between 200 to 1,000 liters.
And this is actually water that's filtered at depth.
Yeah, so our pumps hang down in the water column for 4 or 5 hours. They pump the whole time, and they're pumping through several levels of filter, so we can actually get different size fractions of particles, I brought out one sample today, all 3 different size fractions, so we can take a look at how they came out.
So these came from a single pump?
These came from a single pump from a single depth. This happened to be within the photic zone where there's lots of photosynthesizers, so I'm hoping that when we open them up, they're going to be pretty green. We're doing organic chemistry here, so what you'll see today is a lot of foil that has been baked at a very hot temperature, so it removes all organic matter. And then we use metal and glass implements, and these similarly can be baked at a very high temperature or cleaned with solvents. And we're doing analysis at pretty much a trace level, so we want to make sure that we're removing all other organics. We're not contaminating our samples with anything residual or with ourselves, actually. So that's why we're always wearing gloves or using implements of some sort. These went directly into baked foil on the ship and then directly into a freezer because we don't want any sort of microbial activity to change the organic matter from the time we collect it to the time we analyze it. The only thing that I've done to these so far is that I've cut them up to go to different analyses, and I've freeze-dried them, which just removes all the ice, all the actual water that was left over.
How do you freeze dry it?
In a freeze dryer. So a freeze dryer is basically putting your samples under vacuum at a very low temperature. Instead of melting the ice, the water that's trapped in them goes directly to a gas state and it just leaves the sample. There's no melting. So it removes the possibility of degradation and we end up with a dry sample to analyze. Because any residual water could mess up our downstream chemistry.
Okay.
This is basically my first time opening them up. So I have our 3 different size fractions. We had our very large particles, our fairly small particles that could be anything from a microbe size up to sort of a poop pellet of a zooplankton, and then most of the poop pellets and larger particles are up here. And then we have a very small size that is just sort of a bacterial size and very small degraded organic matter. So I'll start with the small one. We'll probably see some pigmentation because there are actually photosynthetic bacteria that are this small. They're smaller than a micron in size. So open this up. And now I go to my very clean implements and we can just take a look. And I need to be a little more careful here. There we go.
I see something.
Perfect. Yeah. So we've got a little bit of pigmentation on our very, very small particle filter, which is always exciting. They don't always look like anything. So this is our medium-sized particles, and this is where most of our photosynthesizers are.
Oh.
So you can see we've got a lot of nice pigmentation there.
And there's a big difference between the filters from this really fine to this coarser filter.
So this is less than 1 micron in size, so even smaller than most bacteria, only the very smallest bacteria and very small particles. This is 1 micron to 53 microns in size. So let's think, 53 microns is 5/100ths of a millimeter. So very, very tiny. And then finally, our large particle sample.
And I feel like I can kind of see some particles
Absolutely. This is the large particle fraction. Actually, this is a really nice comparison. Yeah, absolutely. These are bigger, half a millimeter size particles approximately. So anything larger than 53 microns. So you see there's a big difference in what we're capturing by doing this size fractionation. And the origin of these particles is different. This is going to be a lot of your photosynthetic microbes. This might be the poop pellets and the sort of degraded, accumulated material, just anything that's sort of floating around and making big chunks. And when we analyze them, we end up with very different chemical signatures between these three different size classes. So the next stage in sample preparation is these filters go directly into some chemicals to be analyzed. So I'm going to cut them up. And this just allows us to sort of make sure that we're getting every component of that filter just by cutting it into small pieces so that they get fully submerged in the acid that we'll put them in. And then once we get everything into vials and start processing it through the chemical stages, we process around 7 to 9 samples at one time. So this upstream end can sort of take a long time to get the individual samples ready for the analysis. And then it takes probably between this stage and the stage where we're ready to put it on the instrument around 4 or 5 days for a set of 7 or 9 samples. That's ready to have some acid added to it, and what that will do is we'll break down all of the complex organic matter that's in these sort of raw biomass particles, and it's going to break it down into smaller units that we then purify further and further to analyze. And I can show you all of the chemical steps.
Where does the filter go?
The filter, okay, so what we do, this is kind of fun because what we're doing through this process is we're obviously going from a solid phase, our samples are actual solid particles, and at the very first stage in chemistry, what we do is we take everything we want and we put it into a liquid phase. And so once we get all of the extracted chemicals into a liquid phase, we can separate out the filter material just by sort of, by actually filtering it through something, and everything we want stays in the liquid. And then from then on, we go to liquid. If we put it on the instrument, we turn it into a gas phase. So we'll get over there too.
Okay.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
Welcome back. We're with researcher Hilary Close, using chemistry to track the path of tiny suspended particles in the open ocean food web. She's using amino acids, which are the building blocks of protein, to follow the suspended particles in the food web.
Now we're doing chemicals. So I've sort of just laid out all of the steps in the chemistry that we need to do in order to get down to the molecules, the amino acids that we're analyzing for this project. So we start out, like I said, with a strong acid, and we heat that at a very high temperature, and that's to break down all of the macromolecules. So proteins are macromolecules, and that's where most of the amino acids are in any type of biomass. So we need to break down that protein into the individual amino acids, and we do that with a strong acid at a high temperature. Actually, between every one of these stages, we're doing some sort of chemistry in the liquid phase, and then we have to dry it back down so that we can do a different set of chemistry in a different liquid phase. So after that first strong acid, we dry it down, we bring it up in a weak acid, and then I can actually get rid of that filter material by pushing all of my filter plus the liquid through a little syringe at the end of this. Once we have that, we do a couple purification stages. We actually make up these tiny little columns just in a little pipette. So we'd fill this with resin and drip it through, and what that does is it just allows the amino acids to come through. There's all sorts of other stuff that might have been released into the liquid when we hydrolyze it on the first stage, and at this point we want to just isolate the amino acids so they're really clean. So we need to get our amino acids into a chemical phase that we can make them into a gas.
Okay.
Which is sort of mind-blowing. So we're going all the way from biomass particles that could include, fish poop, and we're going to measure the isotopes on that gas. The rest of these chemical stages are taking different pieces of the amino acids, different chemical groups that are hanging off that are making it not want to be a gas, and we're adding on other chemistry that allows it to become a gas when we heat it at the right temperature.
The University of Hawaii's Sea Grant College program focused on Hawaii's coasts and its communities through sustainable development, safe seafood supply, sustainable coastal tourism, hazard resilience, and healthy coastal ecosystems. Hawaii's Sea Grant.
Welcome back. University of Hawaii's researcher Hilary Close shows us how she identifies suspended particles in the ocean. Suspended particles are a major component of the food web, which is just beginning to be studied. Hilary reveals their source by breaking down the suspended particles into elemental nitrogen gas.
This is a representation of a protein molecule, and each one of these balls is a different atom of a different element. So it's kind of a lot of stuff put together. They have all sorts of structures. Other proteins can be much bigger, some much smaller. It's a macromolecule, it's complex, and we need to break it down in order to analyze it for isotopes. My particular part of the project, I'm analyzing somewhere around 70 to 80 samples, and it's about the same for the zooplankton and the fish parts of this. So it's a lot of people hours and a lot of resources that go into this, but the data makes it worth it. So
Why? Why is it important?
well, I think the idea behind this project is something that's really exciting, and our results are starting to show that we're gonna have a story to tell with this particular approach in terms of what are the food sources to biota in the deep ocean out here in the Pacific. And that includes looking at, of course, the micronecton, the actual little fishes, and all of their possible food sources, which include these small particles. So yeah, I think that this project is really worth it. Obviously, we put a lot of time into it, so if we didn't think that it was going to be really great results, we wouldn't be excited about doing this. But I'm excited every day when I get to, open up a sample, see how it looks, and start it through the process, and then eventually get over to my results. No matter what we're looking at, if we're looking at fish or zooplankton or particles, they all end up in this little vial at the end. And they all end up in just a little bit of liquid, and then we take them over to the instrument and inject them in. So this is what I was showing you before. All of that water has now been reduced down to this tiny amount of liquid. Can you see that? It's just a little bit yellow.
I can see it, yep.
And so I'm gonna put this in a syringe and inject it. So use a very small volume syringe. Give it a good clean. And actually, there's a robotic sampler on the instrument that could do this instead of me doing it by hand, but these very small samples, these very small volumes, a person is still better than the robotic sampler.
Wow.
So this is a gas chromatograph isotope ratio mass spectrometer. The top part is the gas chromatograph. So what this does is we inject the sample as a liquid at the front of it, and all of a sudden it hits a very high temperature, and that liquid is turned into a vapor. And it's a high enough temperature, and we've done enough chemical processing to our amino acids that the amino acids are actually turning into a vapor themselves.
Oh, wow.
We see fairly large differences in the isotopic content of fish, of zooplankton, and of particles, depending on their source, their original source, and how much digestion they've gone through, basically, how many trophic levels. And we measure that in terms of the isotopic content of the amino acids. And what this is measuring is, like I said, we have the individual amino acids coming out, and then we measure their isotopic content, which is just the number of N15 versus N14 atoms.
So say you had a particle that originated in the deeper part of the ocean, would that be more heavy nitrogen or more light nitrogen?
Right, so that's the kind of thing that we're looking at. So it tends to be that in the surface ocean, it's lighter nitrogen, and in the deeper ocean, because of either degradation or digestion, dietary trophic processes, we get more heavy nitrogen. And that's because light nitrogen is expelled as a waste product, so what you have left over is heavier.
So these suspended particles that you think are really important in this deep sea food web tend to be those heavier nitrogen particles.
Exactly, yeah.
And you can separate the light nitrogen from the heavy nitrogen using this machine?
Yes.
All right.
Okay. Completely. There we go. Right, and started. I'm gonna check my liquid nitrogen. This is always fun when you get to play with liquid nitrogen. So this is a cold trap, just to make sure that we don't get other compounds coming off that will interfere with the signal that we're trying to measure. So you can see these peaks are kind of small, but each of these peaks is a different amino acid, and then the instrument is able to measure the ratios of, like you said, the heavy and the light nitrogen atoms. So this is a really nice first result, and this is telling us that if we measure a fish or a zooplankton that lives, down here at 800, 1200 meters, we could actually tell if they're using as food the larger particles or the smaller particles, because they're very different in terms of those nitrogen contents.
Exploring Our Fluid Earth is a dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group, teaching ocean science concepts through the disciplines of physics, chemistry, biology, and ecology. Exploring Our Fluid Earth is now available freely online. Find out more at exploringourfluidearth.org.